Hello everyone, we're going to talk about limiting reagents and percent yields. And this brings us back to our stoichiometry unit. Like I told you, we're going to be circling back to that now. So we're going to be talking about mole ratios and balanced equations. We're going to have to dust off all those tools that we built near the beginning of the, or rather the end of the last quarter, and revisit those things and then use them in new ways. That's the goal for this. All right, so here we go. So in a chemical reaction, you have reactants and you have products. And as the reaction proceeds, the reactants get used up and the products get created. Now, in an ideal situation, perhaps, all of your reactants would get used up at the same time and nothing would be wasted. But in reality, when a chemical reaction runs, one of the reactants typically runs out first before other reactants do. And that particular reactant is called the limiting reactant. And that's what we see, that's what we're talking about here. So that's what the second bullet point is about, where, excuse me, one reactant in an equation or in a reaction gets used up first. That's called the limiting reagent or the limiting reactant. You'll actually hear both of those terms, reagent or reactant. It's the same thing. And we can use a balanced equation not only to figure out how many moles of one thing you need if you have the number of moles of another thing, but we can use the balanced equation and the mole ratios to figure out which of our reactants is limiting. So let's look at an example. Here is an example. We have hydrogen gas and oxygen gas reacting to form water. It's one of our favorite examples. So using this equation, which reactant will be limiting? In other words, which one do you run out of first if you start out with 4 grams of hydrogen and 6 grams of oxygen? So, and this is the basic structure of these limiting reagent type reactions. Questions. You'll be given the amounts of starting reactants and asked which one runs out first. Okay. The way you do this is to do 2 what-if calculations. One calculation for each of the amounts that you're given. So on the previous slide, we were given 4 grams of hydrogen and 6 grams of oxygen. Those are the two. Those are the 2 starting points that we have. We will use those 2 starting points in 2 what-if calculations, one for each of those. We're going to use mole ratios to calculate how much of the product would be produced from each starting point. And then we look at the results of our 2 what-if calculations. And the what-if calculation that gives us the lesser amount of product is the one that's limiting. That's the one that's going to run out of first. So let's see an example, how this example works out. Here's our equation, hydrogen and oxygen producing water. Here's our question, just kind of reprinted so we can see it. Here's the first step of our process. We're going to do 2 what-if calculations. The first thing we have to do is convert grams to moles. You notice that the question gave us grams, which we can't work with. We need to convert it to moles. So we'll do 2 what-if calculations in parallel. First for hydrogen and then for oxygen, okay? So we start with 4 grams of hydrogen. We use this number, which I hope you recognize as the molar mass for hydrogen, to convert grams to moles. So 4 grams of hydrogen is the same as 2 moles of hydrogen, right? Here's our second what-if calculation, what-if oxygen? Okay, so we start with, as it says up here, 6 grams of oxygen. We need to convert those grams into moles. This is the molar mass of oxygen. So 6 grams of oxygen is the same as 0.19 moles of O2. All right, so now we have our grams converted to moles. That was the first step, convert grams to moles. And now we're going to use mole ratios to determine how much of each product we could make, how much of the product we can make. All right. So, and unfortunately, I flipped these over. So oxygen is now on top and hydrogen is now down here. I hope that doesn't confuse you. You remember from the previous slide, we had 0.19 moles of oxygen out of our 6 grams. All right. So we take our 0.19 moles of oxygen and we use a mole ratio to change moles of oxygen into moles of water. All right, so here are you get 2 moles of water for every 1 mole of oxygen. So the mole ratio is 2/1. That means from 0.19 moles of water, from 0.19 moles of O2, you can make 0.38 moles of water. All right, second what if calculation. You remember from the previous slide, we calculated that our 4 grams of hydrogen represent 2 moles of hydrogen. So we take our 2 moles of hydrogen, we use a mole ratio to convert moles of hydrogen to moles of water. And so we look here, 2 moles of water for every 2 moles of hydrogen. That's where the mole ratio comes from. And so we see that if we started with 2 moles of hydrogen, we could make as much as 2 moles of water. All right. So now we compare, the next step is to compare the two results from your 2 what-if calculations. Which of these 2 calculations, the calculation for oxygen or the calculation for hydrogen, produce the lesser amount of product? Hopefully you can see that 0.38 is less than 2. So in other words, the what-if calculation that we did for oxygen showed us that we could only make 0.38 moles of water. And whereas the what-if calculation that we ran for hydrogen showed us we could make 2 moles of water. So if we were starting with 4 grams of hydrogen and 6 grams of oxygen, our calculations show us that the oxygen will run out first, and we will only be able to produce 0.38 moles of water, whereas the hydrogen is still available because we could have produced as much as 2 moles of water. So oxygen is our limiting reagent, because that's the one that would run out first. All right, we're going to see lots more examples on how to practice this in the worksheet that we do in class tomorrow. All right, so let's move on to our next step. Percent yield. We've kind of done a little bit about percent yield already. I think this popped up in a couple of our labs that we've done. Percent yield is defined as actual yield over theoretical yield. So actual over theoretical times 100 gives you percent yield. Okay? So an actual yield is something that you measure in the lab. You actually do the experiment. That's why I'm calling it actual yield. Theoretical yield is a calculation. You're going to use the balanced equation and mole ratios to determine theoretically how much you could produce of something, or what your yield might be, or maximally be. All right, so actual yield is measured in the lab. Theoretical yield is calculated. Here's our same equation. We use this as an example. So from this above equation, if you started with 2 moles of hydrogen in the lab, how much water would you expect to make? That's how the question is read. But the way you want to think about it is this is just a mole-to-mole conversion that we did before in stoichiometry. 2 moles of hydrogen will get you how many moles of water? Let's see. This is going to give us our theoretical yield. So here's how we do that calculation. 2 moles of water, and the mole ratio, as you can see from here, for every 2 moles of water, there are 2 moles of hydrogen. So that's this mole ratio. If we start with 2 moles of H2, we will produce 2 moles of H2O. That's our theoretical yield. Okay. Now, of course, most reactions aren't perfect. So the theoretical yield is an ideal. It's not anything, it's not actual, it's hypothetical. All right, so theoretically, we could at most make 2 moles of water. But what happens if you actually ran this reaction and you measured the amount of water you produced? All right, maybe, in one example, maybe you only produced 1.5 moles of water instead of the 2 that you expected. So if you actually measured, if you actually did the reaction and you measured how much water you made, in this example, you only produced 1.5 moles. All right, so that is our actual yield. Okay, so in order to calculate the percent yield, you take the actual over the theoretical times 100. So our actual was 1.5 and our theoretical is 2.0 times 100 is 75%. So the percent yield is 75% in this example. Now, of course, obviously, maybe when you run the reaction another time, you produce 1.6 moles of water, and maybe the next time you run it, you produce 1.4 moles of water. So obviously this number can change, but the theoretical yield never changes. The actual yield can change based on different errors and so on that crept into a given reaction, but the theoretical yield will always be the same. All right. So that's an example of theoretical yield percent yield calculations. And again, we're going to be doing some problems like those tomorrow. So go over these two examples that I showed you, be comfortable with them, and we will use them in class tomorrow. That's it. Thank you.